Hello viewers, I'm Kausalya. Today we are going to discuss about the topic measurement of three-phase power using 2 wattmeter method. So this is a common method which is used for measuring power in a three-phase circuits. Right. So the next thing is here for measuring three-phase power we are using only 2 wattmeters. We are not using 3 wattmeters. Right. So whenever we use 3 wattmeters the circuit gets more complicated. Therefore with the help of 2 wattmeters, we can easily measure the power. So here in the wattmeter, there are two types of coil, right? One is known as current coil and another one is known as voltage coil. So here the current coil is used to measure the line current and the voltage coil is used to measure the line voltage. Here, the algebraic sum of the 2 wattmeter readings will give the total power consumed by the load, right? So here that is we have to add, okay, we have to add the readings of 2 ammeters, right? Then the result will give the power. So here the condition is it doesn't bother whether the load is delta connected or star connected, and similarly whether the load is balanced or unbalanced, right? Whatever may be the condition, if we use 2 wattmeters to measure power we can do that easily, right? And finally you see here the total real power. What do you mean by real power or active power? It is the power which is consumed by the circuit, or it is the power which is utilized by the load, right? That is known as real power. So here the power consumed by the load, it is nothing but P1 plus P2, right? That is the value of reading shown in the wattmeter, right? So here the first part is we are dealing with the star connected load, right? And here we are using 2 wattmeters, right? Let this wattmeter be W1 and this wattmeter be W2. And here we are having 3 phases, right? R, B and Y, right? And similarly you see this is your star connected load, right? So here as we all know, you see IR, IB and IY are the respective line currents in the phases R, B and Y, right? And here VR, VY and VB, these are all the respective voltage across their impedances. So here the first thing is P1, it is the reading of wattmeter 1 and P2 is the reading of the wattmeter 2. Right. So generally the power is always given by P is nothing but VI, right? That is our basic formula. So here in this case, you see here the wattmeter is connected with R phase, right? So here P is equal to VI, that is I into R. Therefore here the current flowing through this path is IR, right? Multiplied by the respective voltages. So here you see since the wattmeter is connected in R phase, right? You see this voltage coil is connected between your R phase and B phase. Therefore, here the voltage is nothing but VR minus VB. Right. So, here R is taken as reference or the positive sign. So, here P1 is nothing but, you see, P1 is nothing but IR and the respective voltage here is VR minus VB. So, here P1 is IR into VR minus VB. Right. Similarly, when you look at this wattmeter, this gives the value of P2, right? So, P2 is given by the current flowing through this line is IY. And what about the voltage? You see, this voltage coil is connected between Y phase and B phase. So, here we have to write it as VY minus VB, right? Now, we know the values of P1 and P2. The next thing is we have to add. So, when you add, we can easily find the value of total power. So here it is P1 plus P2. Just substitute the value of P1 and P2. The next step is we are going to multiply. So just multiply and finally we are going to combine the common terms together. So here we are having, you see, here there is a VB term and here there is a VB term. And again both are with a minus sign. So a negative sign is taken commonly outside. Right, let this be your equation number 1. Now the next thing is here the load is, what is the type of load? This is a star connected load. So in a star connected load, what is the basic thing? That is the summation of currents is equal to 0. That is the current flowing through this R phase, current flowing through the Y phase, and current flowing through the B phase. When you add all the three currents, then it will result in 0, right? So because of the star connected load, you see here this is the condition, right? IR plus IY plus IB is equal to 0, and finally IR plus IY is nothing but minus IB, because we need only IR plus IY. Right, now just replace this IR plus IY by minus IB here in this place. So when you replace here, finally we are getting the value as IR VR plus IY VY plus IB and VB. Right, so therefore the total power consumed by the load, right, it is nothing but sum of the instantaneous reading of the two wattmeters. So finally this is the power in R phase, power in Y phase, and power in B phase. Right. So this is equal to the reading shown by the two wattmeters P1 and P2. Right. So here comes the end of this star load. Now we are going to proceed with the delta load. So here this is your delta connected load. Right. So as we all know, delta is nothing but it is a closed path, right? And here again you see IR, IB and IY are the currents that flowing through the lines R, B and Y, right? And two wattmeters W1 and W2 are connected like this. And here you see the respective impedances as well as the current. So this is your impedance value, that is BR. So the current flowing through this line is IBR, and the voltage across this impedance is again VRB or VBR, right? Similarly for the remaining two here. So the thing is, again we are going to find the reading of our wattmeters 1 and 2. So the reading of the wattmeter W1, it is nothing but P1. Okay, so P1, that is power, is nothing but V into I. So here in this case you see again the same thing. The current flowing through this line is IR. Therefore here I is nothing but IR, and voltage is again it is connected between our R phase and B phase. Right. Therefore here the voltage is VRB. Right. Now here the next thing is, you see at node R, that is just this is our node R. So when you apply KVL at this node R, KVL is nothing but sum of current flowing towards the junction is equal to sum of currents flowing away from the junction. So here the current flowing towards R is, this is your IR and this is your IBR. Right, these two are the currents that flow towards R, and IRY is the current that flows away from R. So here just I have written this. Okay, so IR is nothing but, it is nothing but IRY minus IBR. Right, so now we are going to replace this IR value by this expression. So here when you replace, you see P1 is given by VRB into IRY minus IBR. Right. So just for our convenience, you see, I am just reversing the thing, right? Instead of measuring as it as RB, I am measuring from BR, right? So therefore here we are including a negative sign, right? Just for our derivation part, I have done this. So similarly, next we are going to proceed with reading of the wattmeter W2. So it is nothing but P2. So here P2 is, you see again when you look back at this diagram, the current flowing through this Y is IY, and here the voltage coil is connected between your Y and B. Therefore it is VYB. Right. Therefore you see P2 here is given as VYB into IY. Again when you apply Kirchhoff's current law at this node, right? When you apply Kirchhoff's current law at this part, okay, at this node Y, what happens? The current flowing towards this junction is IY and IRY, and IYB is the current that flows away. So here I had written that. Right. So from this again we need IY, right? Therefore when you rewrite this expression, IY is IYB minus IRY. Again just in the place of IY, write this expression. So finally P2 is VYB into IYB minus IRY. Right. So now we had calculated the values of P1 and P2. Now we have to add. So when you just add, you see P1 plus P2 is given by this part, right? So the next step is we have to multiply and we have to combine the common terms together. So here when you multiply, we are getting an expression like this. And again, finally, when you look at these expressions, you see what is a common term. We are having I or Y as common, right? Here we are having an I or Y and here also I or Y. So when you take that I or Y outside, this is our equation. So let this equation be your equation number 1, right? So since this is a delta network, that is a closed circuit, here we are applying our Kirchhoff's voltage law. So Kirchhoff's voltage law is nothing but sum of voltage drops in a closed circuit is 0, right? So therefore here, write down the respective voltage drop across the impedances, right? One is RY and YB and BR, which is equal to 0. So here VYB plus VBR is nothing but minus VRY, right? So here this is our expression, right? So in the place of VYB plus VBR, we can write it as minus VRY. So again, when you simplify, you see here P1 plus P2 is nothing but this is your voltage drop across your BR path and voltage drop across your YB path and voltage drop across your RY path, right? So again, we can conclude that the total power consumed in a circuit is equal to the sum of the wattmeter readings, right? So this is the final thing here, right? So here comes the end of this video. Here we have discussed about two types of load, right? One is delta and another one is star connected load, and it is pretty clear that 2 wattmeters are enough to measure the 3-phase powers, right? So that's all. If you have any doubt, let me know in the comment section. Thank you.